Welcome, gentle listener, to Sleepy Facts. This is a quiet space where the universe tells its stories, not in words, but in light and silence. Here you can rest and let knowledge drift softly like starlight on still water. Let the sounds of the day fade. Feel your breath slow, becoming a gentle tide. Out beyond the window, beyond the soft blue curtain of our sky, lies a vast and quiet dark. It is filled with innumerable stars, countless points of light, each a distant fire burning in the cold. Yet one of them is ours. One of them holds us in its steady gaze, warming our world, painting our mornings, and measuring our days. It is a star we think we know, but tonight we will remember it as if in a dream. A slow, fiery heart beating at the center of everything we call home. This dream begins with light. The light we see is old, even traveling at the greatest speed. The universe allows the image of the sun that warms your closed eyes is from a time that has already passed. It is a memory of the sun as it was 8 minutes and 20 seconds ago, a postcard from the near past arriving now. But the true age of this light, its deeper story, is far older still. The photons that reach us began their journey not from the sun's surface, but from its deep and churning core. For thousands, even hundreds of thousands of years, each particle of light wandered through the dense layers of the star, a slow, patient pilgrimage before it could finally break free and begin its swift, straight flight through the silence of space. The light that touches our world is an ancient traveler, carrying a story that began long before any of us were born. So let us journey there, not with speed, but with stillness. Drifting toward this star, our neighboring yellow dwarf, and entering the ferocious beauty of its atmosphere. We begin on the outermost edge, in a place of impossible heat and ethereal grace. This is the corona, the sun's ghostly crown. It is a vast, wispy halo of plasma, so faint and delicate that it is normally invisible to our eyes, lost in the blinding glare of the sun's face. But on rare occasions during the perfect alignment of a total solar eclipse, when the moon slides like a dark coin to cover the sun's bright disk, the corona is revealed. For a few fleeting moments, it shimmers in the darkened sky. A radiant, silvery white exterior, its tendrils reaching far out into the darkness. It is a breathtaking sight, a secret whispered only when the sun's own voice is hushed. And yet, this beautiful ghost holds a deep mystery. The corona is impossibly hot, hundreds of times hotter than the fiery surface far below it. The temperature here can reach millions of degrees, a paradox that science still seeks to understand fully. Something in this ethereal layer is heating it to temperatures that defy intuition. A quiet, invisible process of immense power. To see the corona in its true detail, we must learn to see in a different light, beyond the colors our eyes can perceive. There are other wavelengths of energy, other shades of the universe. Spacecraft like NASA's Solar Dynamics Observatory are our windows into this unseen world. Looking at the sun through a filter of extreme ultraviolet light, the corona transforms. It is no longer a faint uniform glow, but a complex, swirling tapestry of loops and streams. We see the higher regions of this atmosphere in shimmering detail, revealing the dynamic forces that shape it from within. The invisible becomes visible, and the sun's quiet crown reveals its turbulent heart. Here in this hotter, more active light, we see intensely vivid spots that bloom and fade. These are the sites of solar flares, colossal explosions on a scale that is hard to imagine. Imagine the sun's magnetic fields, immense invisible lines of force generated by the churning plasma deep inside the star. These fields rise to the surface, twisting and crossing over one another like tangled threads. When they become too distorted, when the tension becomes too great, they suddenly snap and reorganize. In that instant, a tremendous amount of energy is released, and the sun spews out an immense wave of electromagnetic radiation. These flares are both terrifying and mesmerizing. Silent, furious blossoms of light that erupt with unimaginable power. But these bright flashes are not the only features shaping the sun's atmosphere. Drifting across the surface, we also see darker regions, places that appear almost empty in this ultraviolet light. These are known as coronal holes. They are not holes in the way we might think, but rather cooler, less dense areas of plasma. Here, the magnetic fields do not loop back to the sun's surface. Instead, they are open, stretching outward like pathways across the solar system. These open fields allow particles of the sun's atmosphere to escape more easily into space. A constant flowing stream known as the solar wind. And when this solar wind, this steady breath from the sun, is directed toward our own world, it collides with Earth's magnetic shield. The particles are funneled toward our planet's poles, and there they ignite the sky, creating the beautiful dancing lights of the aurora, a silent echo of the sun's own restless energy. There are other forms born from these magnetic fields, other shapes made of light and fire. Great loops of plasma known as solar prominences rise from the sun's surface. They are enormous arching structures, so large that our own Earth would be a tiny speck beside them. These shimmering filaments can stretch for hundreds of thousands of kilometers into space, tethered to the surface by magnetic forces. A prominence can form in as little as a day, a glowing bridge between 2 points on the sun. If it is stable, it can remain in the corona for months, a silent, fiery monument against the blackness of space. Watching them move, even in sped-up time, is to witness the immense speed and power of the sun's magnetic heart, as it lifts and shapes seas of plasma with an invisible, effortless hand. And sometimes, in the sun's high atmosphere, it rains. Not all of the charged plasma fired into the sun's corona continues its journey out across the solar system. Some of it remains trapped in the magnetic loops of the corona. Slowly it cools, condensing and growing heavier until gravity gently pulls it back down. It falls toward the sun's surface as a shining, silent shower of coronal rain. It is a beautiful sight to imagine. But this is a rain of fire, still millions of degrees in temperature, falling softly back to the star from which it came. But a gentle return is only one possible fate for the sun's rising plasma. Here, the quiet metaphor of earthly rain ends. On Earth, clouds do not suddenly snap like a released elastic band, firing their substance into space. But on the sun, thanks to those tightly wound magnetic fields, they do. Sometimes, a structure of plasma and magnetic energy will build and twist at the sun's edge, growing more and more unstable until it finally breaks free. This is a coronal mass ejection, a moment when the sun releases billions of tons of its own plasma out across the solar system in a single explosive burst. It is one of the most powerful events our solar system knows. A vast, expanding cloud of charged particles traveling at immense speeds. If a powerful one were to strike our world, even with the protection of Earth's magnetic field, it could be devastating for the delicate web of satellites and electrical grids we rely on. It is a reminder of the sun's untamed power, a force that both gives life and holds the potential for immense disruption. All of these structures, the quiet loops, the searing rain, the explosive clouds, are seen in a light that corresponds to the extreme ultraviolet part of the spectrum, and their appearance is not constant. They are more common in some years than in others, their frequency tied to the rhythm of the sun itself. The sun has a cycle, a slow 11-year pulse during which its activity rises to a peak, the solar maximum, before falling again to a quiet minimum. These phenomena are the visible signs of that deep internal clock, the outward expression of the star's own changing seasons. And just as our eyes see only a fraction of light, A single wavelength tells only a fraction of the story. To truly understand the sun's atmosphere, we must look at it from many perspectives at once. Imagine two images of the sun's corona taken at the exact same time, but with different filters of light. The first image at a cooler temperature shows the quiet corona, a place of calm, graceful loops of magnetism. The second image at a much hotter temperature reveals something entirely different. The calm loops vanish, and instead we see the fiercely bright active regions, the very places where flares are born. What appears as a single phenomenon is revealed to be a complex, intertwined chain of events happening at different temperatures in different layers. One view shows the peace, another shows the fire. Both are true at the same time. And with all we have seen, we have still not technically made it through the sun's atmosphere. Our journey moves ever inward, deeper into the layers of light. We descend now to the transition region, a very thin layer only about 100 kilometers thick that sits between the incredibly hot corona above and the cooler layers below. Here in this shallow boundary, the temperature changes dramatically. It rises from around 8,000 degrees to 500,000 degrees. For a comparison, on an earthly scale, the fiercely scalding lava erupting in Hawaii is just over 1,000 degrees. The lower end of this thin solar layer is almost 6 times hotter than that, and the upper end is more than 300 times hotter. It is a place of intense, sharp change, a thin, invisible wall of rising heat. Traveling even deeper, we find ourselves immersed in the sun's chromosphere, the last layer of atmosphere before we reach the sun's visible surface. It is a thicker layer stretching for nearly 2,000 kilometers. Inspecting it closely in its own shade of ultraviolet light, we identify some of the most mesmerizing features of all. They are known as spicules, long thin jets of plasma that sway like tall, wavy grass, blowing in a celestial wind. These jets shoot upwards from the sun's surface at incredible speeds, hundreds of times faster than the speed of sound. They can reach heights taller than our own Mount Everest, forming and vanishing in only a few minutes. For a long time, their origin was a mystery. It wasn't clear how these magnetically charged particles could escape the sun's powerful magnetic fields at this level of the atmosphere. The answer, when it was found, was unexpected. Early models had not included neutral particles, thinking they wouldn't affect the motion of the charged plasma. But once they were added, it became clear that these neutral particles gave the charged particles an unexpected buoyancy, the lift they needed to break free and shoot upward into these beautiful, fleeting spicules. And so we drift deeper still through this field of swaying, fiery grass. The swaying spires of plasma fade below us, and we descend at last to the photosphere. the surface of the sun. In our telescopes, viewed in the soft glow of visible light, it is the layer we know best. From our great distance on Earth, it seems to have a clean, precise edge, like the shore of a calm, golden sea. But this is an illusion born of distance. The sun is not solid at all. Here, matter is too hot to be solid or liquid, or even gas. It can only be plasma, a shimmering soup of ionized atoms and free electrons which makes up almost all of the visible matter in the universe. The photosphere is the outermost layer of this plasma sea, a boundary that is not fixed but constantly shifting. And sadly, it is the deepest layer of the star which our instruments can measure directly. What lies beneath it remains shrouded in a beautiful mystery. But even here, on this visible surface, there are stories to be found. As we look closer, we notice dark spots, islands in the sea of light. These are the sunspots. They appear darker only because they are cooler than their scorching hot surroundings, though still unimaginably hot by any earthly standard. Unlike the coronal holes we saw in the atmosphere above sunspots form in areas where the magnetic fields are particularly powerful and dense. Here, the intense magnetism traps heat beneath the photosphere, slowing the convection that would normally bring it to the surface. They are the footprints of the same immense magnetic fields we saw arching through the corona, their roots visible now as dark patches on the sun's face. And when we compare this view of the sun in visible light with the one we saw earlier in extreme ultraviolet, a connection emerges from the deep. The locations of the captivating solar flares and the quiet sunspots coincide. They occupy the same space. From this, it becomes clear that one must lead to the other. A deep, tangled energy that rises to the surface and then, in a flash, releases itself back into the cosmos. Let us look closer still at this surface, at the very texture of the sun's skin. Next to and surrounding the sunspots, the photosphere is saturated with jagged-edged, endlessly shape-shifting cells. It looks not unlike lava as it cools and cracks a mosaic of light and shadow. But these cells, known as solar granules, are around 1,000 kilometers wide. They are the visible tops of a vast churning convection cell moving underneath. The brighter areas inside each granule represent fluid of unimaginable temperatures rising from the sun's interior to its surface. Upon reaching this boundary, the fluid has nowhere to go except to spread outwards across the cell. As it spreads, it gradually cools and then sinks back inwards along the rough dark boundaries that surround each cell before beginning the cycle once more. It is a process that closely resembles the convection currents deep within the Earth's own mantle, the slow engine that drives our continents. This is the sun breathing. And while this process may look slow and gentle from afar, it is not. Each granule lasts for as little as 20 minutes, a brief, fiery lifetime. The flow of plasma within these cells reaches supersonic speeds, moving faster than the speed of sound, generating silent waves that ripple across the sun's surface, the echo of countless sonic booms. And when we pull our gaze away back to the full disk view of the sun we saw before, an image that might look quite grainy even from a high-tech space probe, we realize now what we are seeing. That graininess is not a processing effect or excess noise in the image. That graininess is the granules themselves, countless millions of them covering the entire photosphere, the very texture of the sun's living, breathing skin. And here, our inward journey must pause. For we have reached the deepest layer of the star that scientists can yet image using either visible or non-visible light. Much of what lies beyond this layer remains a secret, waiting for a time when we can dream of new ways to see. But looking back on the journey so far, we can see the quiet beauty of using light of all different spectrums. They help us observe exploding solar flares, vast coronal holes, swaying spicules, intriguing sunspots, and these shape-shifting cells, each in completely new ways. The sun is abuzz with lively activity, and so much of it would be invisible to us were it not for these other ways of seeing. It fills one with a gentle curiosity, knowing there is so much going on unseen in the universe, and knowing we have found the means to uncover it. This constant activity is not chaotic. It follows a rhythm, a deep, slow heartbeat that pulses through the entire solar system. The sun operates on an 11-year cycle, alternating between a period of low activity, the solar minimum, to a much higher level, the solar maximum, and then back again. Sunspots, solar flares, and the great coronal mass ejections all become more common during the solar maximum. You are 50 times more likely to see a solar flare during the sun's peak than during its quietest time. These cycles are woven into the very fabric of the star, and this 11-year rhythm is only one half of a larger, deeper cycle known as the Hale cycle. This cycle maps the changes in the sun's magnetic polarity. Once every 11 years, at the peak of a solar maximum, the sun's magnetic North Pole and South Pole swap places. When another cycle occurs, 11 years later, the poles swap back again to where they began. Tick, tick, tick. This constant rising and falling of solar energy thrums through our planetary system, rising and falling like a quiet cosmic heartbeat. We do not fully understand why the sun goes through this cycle. It is clearly related to the magnetic processes deep within the star itself. But for all our watching, the reason for its particular length remains a mystery. This constant rising and falling of energy thrums through our planetary system like a quiet heartbeat. And surprisingly, even from so far away, we here on Earth move to its rhythm. It begins with the space around us, a space that is growing more and more a part of our modern world. When the sun is in its active phase, the solar maximum great clouds of plasma, the coronal mass ejections, stream out more regularly. Scientists can often see them coming, watching their approach for days, sometimes weeks in advance. This quiet warning allows those who travel in space, our astronauts, to find safe shelter from the rising levels of radiation. It also gives us time to power down the delicate hardware on the thousands of satellites that drift in orbit above us, protecting their sensitive circuits from being overwhelmed. A solar storm can cause unexpected electrical currents to form in their fine wiring, a gentle surge that can overload systems that have not been put into a safe sleeping mode. There is another more subtle effect. All of that radiation has an impact on our own atmosphere. It warms it just a little. And as the atmosphere warms, it expands. It blossoms upwards like a flower opening to the sun. For the satellites in low Earth orbit, this means the thin, almost non-existent air around them suddenly becomes a little thicker. The whisper of drag that was once barely there is now a gentle but persistent friction. Normally, these satellites only need to correct their orbits a few times a year, a small push to keep them in place. But when a geomagnetic storm occurs, the atmosphere blossoms, and they must maneuver every few weeks to keep from slowly, gently falling from the sky. Sometimes, this gentle friction is enough. There have been times when a powerful storm has caused a satellite to slow just enough to be pulled back into the atmosphere. Its mission ended by a sudden, invisible atmospheric tide. The radiation can also influence our ionosphere, the high electrically charged layer of our sky. It fills this layer with more plasma, which can have a slight lensing effect on the signals that our navigation systems rely on. The next time you look at a map on your screen and it thinks you are a street away from where you truly stand, a quiet geomagnetic storm might just be to blame. Our power grids, those vast networks of wire stretched across continents, also braze themselves every 11 years. The currents induced by a storm can cause them to become overloaded, so they must be watched with care. And for those who listen to the sky, amateur radio enthusiasts and airline pilots, their high-frequency signals can be deflected or even blocked by this more powerfully charged ionosphere. It is as if the sky itself becomes a little harder to hear through. But there are bright sides to this celestial weather. As the sun's breath becomes more turbulent parts of the world closer to the poles, see a rise in the number of auroras dancing hypnotically across the night sky. Those who chase these lights report seeing them go from a few times a year to as many as twice a month during the most energetic parts of the sun's cycle. The sky puts on a quiet, shimmering show, a gift from the sun's own restless heart. And you might think that is where the influence ends. That the sun's cycle might touch our machinery, but not the living things of our world. But the connection runs deeper still. Some of this is incidental. When the sun is at its quietest, its solar minimum, it exerts less pressure through its solar winds. This means our heliosphere, the protective bubble the sun creates around our solar system, offers a little less protection from deep space cosmic radiation. This form of radiation is highly energetic, but fortunately, it rarely makes it all the way through our atmosphere. But reaching the atmosphere is all that is needed to produce an effect. There is a theory, still a gentle whisper among scientists, that this extra radiation could be creating tiny nucleation sites in the air, seeding the formation of extra clouds, a subtle link between the quiet sun and a cloudier sky. Even without that, during the solar maximum, the space weather hitting our atmosphere can raise global temperatures just slightly, less than half a degree, and the temperature always returns to where it started. But it is enough that it can be noticed, especially by the species who pay close attention to the turning of the seasons. Studies of birds have shown that in these warmer years, they tend to lay their eggs a little earlier. And curiously, one study found that the laying times of blue tits were also affected by the number of sunspots on the sun's face. A connection that even the researchers found hard to explain. It is not as if birds can look at the sun and count its spots. And yet, a link seems to exist. A quiet, invisible rhythm felt in the nests of sleeping birds. This is not something that affects only birds or other species sensitive to magnetic fluctuations like homing pigeons, who are known to fly different routes depending on what time in the 11-year cycle it is. The influence may touch us too. There are numerous quiet studies on how these solar cycles might influence human health. One spanning 2 decades, and a third of the women in Holland discovered a slight peak in certain health conditions that took place just after the solar maximum, when the sun's radiation was at its strongest. Another study looked into the rate of mental disorders and found that those born during higher energy, more chaotic solar cycles experienced a very slight increase in these conditions. If this is the case, then the state of the sun at the moment of your birth might have influenced the course of your life, not in the way of star signs and horoscopes, but in a subtle physical way. A faint imprint left by the rhythm of our closest star. It should be stressed and stressed gently that any health impacts caused by these cycles are extremely minor. As one researcher put it took hundreds of thousands of patients to even notice that there was a health impact. The sun's cycle should not prevent you from living your life. And living through or being born in a solar maximum is not all shadow. The same studies suggested that this extra energy, this radiation, might also lead to a rise in creativity and adaptability. Perhaps it was during one such cycle, 80,000 years ago, that a human brain was gently nudged, mutated in a way that gave it abstract thought and consciousness. If so, if this cycle gave us the very means to perceive the universe, then we have much to thank these solar maximums for. We would not be us without them. The thought remains a quiet wonder. The sun speaks to us in light, in heat, in these silent, pulsing rhythms. But what if it could speak to us in sound? It is a simple enough question, and it comes with a simple enough answer. The sun is silent. Sound, as we know it, needs a medium to travel through, air or water, something to carry its vibrations. In the near-perfect vacuum of space, there is nothing. And so, to us, the sun sounds like nothing at all. But let us set aside this simple answer just for a moment. Let us imagine that space could carry sound, that there was no giant cosmic muffler between us and our closest star. What would we hear? Would the sun sing to us, an enchanting melody in our sky? Or would its noise be so immense, so cataclysmic, it would instantly be the last thing we ever heard? Scientists, in their own quiet way, have found the answer. Through spacecraft like the Parker Solar Probe, which is even now making skimming orbits around the sun, they can detect the pressure waves and particles emitted by the star. And they can convert those waves, their amplitudes and frequencies, into the sounds we might hear, if space were capable of carrying them. And interestingly, not all of the sun's sounds are the same. So let us listen in our imagination to the different sounds the sun makes, recreated through clever science. Because it turns out that these sounds may hold the key to solving two of the sun's greatest mysteries. In our imaginary world, where space has suddenly gained the ability to propagate sound, we can begin to listen to the sun all the way from Earth. And even from 152 million kilometers away, the sun is very, very loud. It would sound something like a deep, soothing buzz, a hum with an almost electrical feel to it. It might remind you of generators or perhaps something vaguely radioactive. which is appropriate given that this is the sun we are talking about. The nuclear fusion going on deep inside its core is releasing an amount of power that is difficult to comprehend. This power has a direct effect on the volume of the sound the sun would produce. Imagine the device you are listening on now, connected to the speakers they use at a rock concert, played at full blast. The sound would be loud enough to cause permanent hearing damage to the entire population of the planet. If it were to play in our sky non-stop, we can consider it extremely fortunate that we do not actually have to deal with this. In such a world, species might have evolved with no ears at all, as hearing would be pointless. And if we were to get closer to the surface of the sun, that sound level would grow exponentially. It would become so loud, it would be 100 million times higher than the physical cap on sound that our own atmosphere can convey. The sun is loud, which is a shame, because some of the sun's more delicate sounds can only be differentiated when we enter that ear-splitting zone. By the time the noise of the sun has reached us here on Earth, many of its individual sounds have blurred into one meaning. We miss out on their fascinating intricacies. So to gain a better insight, we would need to get closer. Let us in our dream ignore the volume of the sun for now, and instead let us focus on its sound patterns. If we were to enter a spacecraft and head toward the sun, we would soon begin to hear a difference in the sound's uniformity. Rather than a constant steady buzzing, we would begin to hear something more like a rustling, a shifting, flowing sound. This is the sound of the solar wind. The sun emits a constant stream of charged particles that blasts out across the solar system, and its existence represents one of the sun's greatest enigmas. You see, it is tempting to think of this stream as starting deep inside the sun and blasting outward under the incredible force of all that nuclear fusion. But through observation, a strange discovery was made. Particles within the sun's atmosphere, the corona, are moving around at a certain average speed. But particles just outside of the corona are traveling much, much faster. This means that particles with enough speed to escape from the sun's surface are drifting into space. And then something in the sun's corona is hyper-accelerating them from subsonic to supersonic speeds and firing them off across the solar system. What kind of process or mechanism is doing this remains a mystery to this day. The corona, as we know, contains a second enigma too. It is far, far too hot. The surface of the sun has an average temperature of about 5,500 degrees Celsius. But within just a few kilometers as you enter the corona, the temperature suddenly jumps to as high as 2 million degrees. Something in the sun's corona is flicking solar wind into space, and something is making things very, very hot. Scientists do not know why this is happening, though it is thought to have something to do with magnetic fields. And it is here that we would meet the third sound of our tour. As our spaceship draws closer and we pass over the boundary between the corona and empty space, we would begin to hear a new sound, a high, whistling, ethereal tone. These are known as Langmuir waves. They are formed by tiny oscillations of plasma particles, vibrated by light itself, as they stream from the sun through tiny funnels on the sun's surface. It is the magnetic equivalent to the sound a kettle makes as it boils. The sun's exterior is covered in islands of hot material rising from the star's center. Once there, the material cools and sinks back into the star. And something about this process makes these sinking zones stream out powerful magnetic field lines. Plasma is scooped up by this magnetic force and sent streaming into space, the very starting point of the solar wind. Scientists do not yet know what causes this process, but the sound of these Langmuir waves is eerily beautiful. As these winds head out, not all the waves created in this way travel at the same speed. This has the effect of spreading out the sounds as faster parts of the wave run ahead, while slower parts fall behind. This creates what are known as dispersive waves, waves filled with chirps, little eddies of sound where fast waves coming from behind meet slow waves already traveling ahead. Eventually, this all evens out into the steady hum we first heard from Earth. There is one last sound, one that might offer an insight into this entire mystery. Here, right within the sun's boiling corona, we can finally begin to detect it. They are known as Whistler mode waves. Whistler waves are the distant echo of high-energy events that ring through the plasma of a celestial body's magnetosphere. We get them here on Earth whenever lightning cracks. You get more than just thunder. A ripple travels through our planet's magnetosphere that can be picked up kilometers away with the right detectors. On Earth, they sound like a few small little cracks and whistles, nothing too special. But on the sun, they sound like a cacophony of wailing wind. To go from sparse, brief clicks to one incessant, roaring wail indicates that the sun's magnetosphere is not just experiencing the odd crack of lightning. Something is going on constantly all over the star, merging individual moments together into one great roar. Scientists are still trying to figure out what that roar is being caused by. But there is a theory, one that can account for the dramatic acceleration and the superheating of matter within the corona. It is a dry-sounding little event called magnetic reconnection, and yet its innocent technical-sounding name disguises a cataclysm. The sun is a tensely wound up ball of shifting magnetic field lines. When these lines travel away from the sun, it is sometimes possible for them to merge with other field lines, creating those iconic loops that you have likely seen in images of the sun. However, at the moment such arcs are formed, all hell breaks loose. When two parallel lines touch, creating an arc, there is a massive realignment in the excess field lines. Cut from their tethers, the field lines further out from the sun form an arc of their own, which then catapults off into space like the releasing of a gargantuan stretched rubber band. This rapidly accelerating magnetic force is known as a nanoflare, and it indirectly heats the corona above it to multi-millions of degrees in seconds. Scientists have only recently developed the capability to even see these nanoflares, and it is not yet completely understood. And still, it is not completely far-fetched that such moments when the sun gets so wound up that it snaps. Explain why its corona is as hot as it is, and why it is flinging solar winds out across the solar system with such force. To account for the constant roar and the constant solar wind, these nanoflares would have to be happening all the time all over the sun. A constant, widespread storm of snapping, releasing energy. The sun continues to hold many mysteries. But the Parker Solar Probe continues its journey, gathering valuable data with every pass. Perhaps it will find more sounds for us, each one a clue to the ancient riddle of how the universe works. Because ironically, just like listening to the ticking of a clock to try and figure out how the clockwork functions, the secrets of the sun might one day be solved by what we hear rather than by what we see. And sometimes what we think we see is not there at all. It is something hardwired deep within us, this desire to be remembered. For thousands of years, people have erected monuments to themselves, performed great deeds, all to endure after they had passed on. It is no wonder then that some people might want to be the one who made a great scientific discovery, like discovering a special star or a new planet, so they would be remembered for all time. But being overzealous, wanting something too much, could lead to being remembered for all the wrong reasons. Let us rewind our dream to the year 1846. Something astounding had just happened in the scientific community. A French astronomer and mathematician had just helped discover the planet Neptune using nothing but pure mathematics. He had been examining the orbits of the then 7 planets when he noticed that something was off about Uranus. It did not seem to be moving in line with the theories of gravity that were understood at the time. He reasoned that the only explanation was that there must be another planet out beyond the orbit of Uranus that was gently pulling on it, perturbing its motion. So he did the maths and then declared that his 8th planet must exist at an exact point in the night sky. And incredibly, after hearing this prediction, a friend of his got out a telescope, searched in that location, and sure enough, discovered the planet Neptune in a single hour. It was almost exactly where he had predicted it would be. The scientific community was alight with this discovery, and the astronomer Leverrier was rightly celebrated for his incredible deductions. So it is not surprising that a decade later, when he predicted the location of a ninth planet using the exact same methodology, the scientific community listened. In truth, he was not the first to predict that such a planet existed. For centuries, various astronomers had claimed to have noticed a strange black spot moving in front of the sun, something they claimed was a new planet closer to the sun than Mercury. In reality, what they were likely seeing was a sunspot. But people had even begun to suggest a name for this hypothetical world, Vulcan, after the Roman god of volcanoes and fire. It would have been an appropriate name. Any planet closer to the sun than Mercury would have been exceptionally hot. And yet, for all these sightings, confirmation of the planet remained elusive. But what made Leverrier's claim stand out was the way he had come to make it. Years before his discovery of Neptune, he had been asked to apply the known laws of physics to the orbit of Mercury to see if the two lined up. He laid out a theoretical orbit that Mercury should take around the sun. And once his prediction was made, astronomers observed Mercury to see how well it matched. Only it did not. So Leverrier tried again, reasoning that perhaps his maths had been out. He did a much more thorough study using multiple observed sightings of Mercury as his baseline. He once again mapped out Mercury's orbit, but once again, his predictions were out. Not by much, only 45 arc-seconds per century, but enough that there was conclusively something strange going on. Confident of his maths, this time Leverrier reached the same conclusion he had with Uranus. There must be some other mass pulling Mercury out from its idealized orbit, either a planet or a series of asteroids. Given his success at locating Neptune, many astronomers believed him, and so they rushed to their telescopes to try and spot this alleged planet. Spotting a world so close to the sun was inherently difficult. The glare of our star would completely obliterate the reflected shine of a tiny planet. So the most effective method was to see the darkening it caused as it traveled across the sun's face. A transit. And in 1859, an amateur astronomer claimed to have seen just that. He had used basic tools in a homemade observatory and claimed to have spotted a small black object passing by the sun. He wrote to Leverrier, who was so taken by his claim that he traveled by train to the man's home unannounced to verify it. He questioned the amateur, heard his observations, and came to the conclusion that the man was telling the truth. And so, the two of them announced the discovery to the world. They named the planet Vulcan. The scientific community was once again very impressed. But there was only one problem. The planet that had been discovered did not actually exist. There were numerous proofs of this. For one, other scientists naturally wanted to take a look at this new planet. Leverrier calculated from the amateur's observations that Vulcan must orbit the Sun every 19 days and 17 hours. So it would be easy to spot, as it would be calculable when it would pass the Sun again. Astronomers pointed their telescopes toward the Sun at the appointed time, but Vulcan was a no-show. Leverrier was troubled by this, but by then, more reports were coming in of the planet's sighting. Other astronomers were going back through their records and were matching up phenomena they had seen with this new planet Vulcan. Some of these records were years out of date and not even listed as to when in the year they had happened. But Leverrier still used them to tinker with his model reasoning that perhaps his maths were just out. So he would predict and would not see Vulcan and would rework his theory and would not see it again. Another piece of damning proof came from another French astronomer. He claimed that he had been coincidentally looking at the Sun at the exact same moment as the amateur observer, with a telescope that was twice as powerful, and had not seen the planet. Vulcan's existence floated through these murky waters, as there were renowned scientists who did claim to see it from time to time. Even a year after Leverrier's death, two well-renowned astronomers both claimed to have seen Vulcan at the same point in the sky at the same time during a solar eclipse. The cooperation was compelling. Yet, Vulcan still did not exist. In science, if a fact is true, then it is repeatable. And in spite of all these observations throughout the years, Vulcan was never repeatedly observed. It was never seen during a solar eclipse again. In time, that corroborated sighting was put down to calculation errors and misidentifying a known star. But ultimately, the one who finally put the idea of Vulcan to rest was Albert Einstein. And he did so by thinking of something completely different. Numerous scientists over the years had attempted to see Leverrier's planet Vulcan because mathematically they were certain it had to exist. The old laws of physics demanded that it did. They strained to see it, and in that confirmation bias, they did see it again and again, just never in the same place. But Einstein realized that it was the old physics that was at fault. In 1915, he proposed a new model of physics, one that relied on things like the curvature of space-time rather than gravity. And sure enough, Einstein's new model predicted the exact orbit that Mercury made around the Sun, deviations and all. And with that, the case for Vulcan's existence evaporated. Under this new understanding, it couldn't exist. There could be no object next to the Sun of a planetary size, or it would mess with Mercury's orbit, so that it would no longer line up with the maths. There is a lesson in this somewhere. Sometimes, if we want something too much, we find it, regardless of whether it is really there or not. Sometimes, it takes thinking outside the box and challenging our previously held beliefs before the truth can be found. The truth does not need our fervor. It will prove itself given time and opportunities for repetition. And so, Vulcan, a planet of fire, was nothing but smoke and mirrors, a yearning for something, but never a reality. And sometimes, what we see in the sky is real, but so strange, it makes us wonder if we are dreaming. Perhaps you have seen what looked like a rainbow, only it was upside down, a gentle smile of color in the sky. Or maybe you have seen a perfect circle of light around the sun, with two soft splashes of rainbow color on either side. These are not dreams. They are a unique category of optical phenomena called ice halos. Though similar, they are not technically rainbows, but their own distinct wonder. Some are relatively common, while others are extremely rare. As you might know, rainbows occur when sunlight is refracted by liquid water droplets suspended in the atmosphere. But what happens when that light hits water particles that are made of ice rather than liquid water? Depending on the shape and orientation of the ice crystals, as well as the direction of the light hitting them, they can produce a whole range of beautiful optical forms. To date, 119 kinds of ice halos have been categorized, and there may still be others we do not yet know about. Most circular halos are made by tiny ice crystals in high, thin cirrus clouds. These clouds occur high in the troposphere, usually 5 to 10 kilometers above the Earth's surface, where temperatures are very cold. As a result, halos can be seen anywhere on Earth all year long, even in very hot climates. The ice crystals themselves are small and remarkably uniform in shape. This regularity has to do with the very structure of ice on a molecular level. When water freezes, its molecules slow to a halt, and the bonds between them become fixed in a hexagonal lattice structure. This highly organized structure is what causes the ice particles to form hexagonal crystals. Some are flat like tiny plates, while others look like columns with a hexagonal cross-section. It is the extreme regularity of the angles between the faces of these millions of crystals that allows them to scatter light with the consistency needed to produce a halo. These halos are sometimes quite colorful. That is because when the ice crystals refract the light, the red and blue frequencies bend at slightly different angles and disperse. In some halos, two colorful spots are visible to the left and right of the sun. These beautiful phenomena are called parhelia, or more commonly, sundogs. Sundogs appear when the ice crystals are shaped like hexagonal plates and they take on a horizontal orientation as they gently fall through the air. Sometimes, sundogs are accompanied by another optical phenomenon called a circumzenithal arc. These arcs look similar to rainbows, only they are upside down, which gives them a friendly smiling appearance. These arcs appear high above the sun, and only when the direction of the light and the orientation of the ice crystals are just right. Because these ice crystals function essentially like a 90-degree prism. The color separation is excellent, meaning these arcs have a far higher degree of clarity than actual rainbows. And if you are really lucky, you might even spot one at night, accompanying a halo around the moon. They are called lunar circumzenithal arcs, and they only appear when the moon is extremely bright and fairly low on the horizon. A gentle, upside-down rainbow in the middle of the night. These beautiful circular halos have also been sighted on Mars. An image taken by the Perseverance rover showed a faint halo around the sun in the Martian sky. This has led some to suggest that the cause may be not water ice, but carbon dioxide crystals in the planet's cold, thin atmosphere, or perhaps a mixture of both. The size and appearance of these halos provide clues about the types of crystals forming in the atmosphere of other worlds. And so scientists hope that by studying halos here on Earth and spotting them on other planets, it could shed light on the composition of those planets' atmospheres. If you wish to see one for yourself, here are some things to look for. First, check for those high-altitude wispy cirrus clouds, the ones that contain the small ice particles needed to produce a halo. Then look toward the sun or moon, but take care not to stare directly at the sun. While rainbows form in the part of the sky directly opposite the sun, most ice halos form in proximity to the sun or moon. And while they tend to appear in fair weather, they often arrive at the front of an approaching storm system. Meaning, if you see one, it is better not to linger outside for too long. If the weather is fair, but you see rain in the forecast for the next 24 hours, keep an eye on the sky. Your chances of seeing a halo will be higher. Of course, the best way to see one is to look up every day. Ice halos can form anywhere on Earth. So if you keep looking, you are bound to see one sooner or later. And as the sun shines through these high, icy clouds, it also illuminates other travelers in our solar system. Wanderers made of ice and dust, drawn from the far reaches of space. These are the comets, and some of them are on a path that will take them perilously close to the sun. These are the sun grazers. They are comets that do just that. They graze the sun as they pass, with the closest parts of their orbits, taking them within a hair's breadth of the sun's surface. Often, they will pass right through the sun's huge atmosphere, the corona. These comets are mainly long-period comets, their orbits taking hundreds to thousands of years to complete. Because of their orbit's extreme elliptical nature, they build up tremendous speeds as they approach the sun. The majority of these sun-grazer comets actually all originate from one large comet that was ripped apart several hundred years ago. Over time, the fragments from this larger comet have spread out, meaning there is probably a steady, quiet flow of them. And as the largest of these comets also pass by the sun, they too break apart into even smaller comets. We believe this because they all tend to follow the same orbital path. The brightest comet in the last millennium, known as Comet Ikea-Seiki, was probably one of these fragments. It was so bright as it approached the sun that it could even be seen during the day. Another famous fragment of this same comet dimly illuminated the sky in the southern hemisphere in 2011. It was called Comet Lovejoy. It was not expected to survive its encounter with the sun, as it would have been in the sun's 1 million degree corona for more than an hour. However, astonishingly, it fizzed away from the other side of the disk, mainly intact, though probably severely impacted from the experience. The same thing happened to another comet called Ison. It was expected to be a bright comet potentially visible to the naked eye when it passed by the sun in 2013. Alas, that was not to be. However, it still made for good viewing for the sun-observing satellites. Ison's approach was bright and impressive, and upon reaching the other side of the sun, it faded out. Scientists cannot be sure if its nucleus survived or not. But if it did, there are certainly no volatile substances left on it. All that is left is probably dust. These are some of the biggest sun-grazer comets we have ever observed. Some of the smaller ones, only tens of meters across, were not known about until they actually came into the view of a sun-observing satellite. Many of these smaller comets were completely snuffed out by the sun immediately after passing too closely. Which means, unfortunately, they were vaporized pretty much immediately after they were discovered. At this distance from the sun, the heat is incredible and the gravity is overwhelming. The icy comets not only evaporate quickly, but the rocky elements of them are also ripped apart by tidal forces. Even the largest sun-grazer comets will come away heavily scarred. There is an interesting phenomenon that happens when a sun-grazer passes by the sun. Often, a coronal mass ejection will go off at the exact moment the comet passes. However, scientists are of the opinion that there is no mechanism for a sun-grazer to cause a CME. These comets are simply not big enough to have any consequential impact on the Sun. So it is currently believed that these examples are purely coincidental. What scientists enjoy about these sun grazers, though, is that while we cannot send probes deep into the Sun's corona, it is simply too hot for that. We do have these thousands of comets that are willing to take the plunge for us. And comets are perfect for us to observe what we are looking for, which is to better understand the magnetic fields within the corona. As a comet passes by, its tail wiggles. The particles in the tail get heated so much, they turn to plasma, and plasma reacts strongly to magnetic fields. So the wiggle you see in the tail is believed to be due to the way in which the tail interacts with the magnetic field lines in the corona. As more comets pass through, the more we will begin to understand that environment. And so these icy wanderers in their final moments give us a gift of knowledge, a last fleeting glimpse into the Sun's fiery breath. The light from these passing comets is a soft, fleeting thing. But have you ever wondered what it would be like to have two suns in our sky? Seeing two suns during a sunset would be a spectacular sight. And it is not such a rare occurrence in the universe. It is currently estimated that 1/3 of all star systems have two or more stars, which makes one wonder, how much would having a second star impact us here on Earth? How hot would our world get? What would the day and night cycle be like? Would it be possible for life as we know it to survive? Well, it depends. Let us keep our sun as it is and only make the second star the variable in this thought experiment. Stars, as we know, come in all sizes, from small, cool, and dim red dwarfs, all the way up to large, hot, and bright blue supergiants. In a binary star system, the stars orbit around the system's center of mass. Let us say we place a red dwarf, which is the smallest type of star, in a close orbit around our sun. Even though a red dwarf can be as little as 7.5%, the mass of our sun, it would already have a big impact on us. Our year would be shorter. Because of the increase in mass and gravity of the system, Earth's velocity would have to be faster in order to not be pulled into the stars. The increase in temperature from this second star would also be noticeable, likely making it unbearable for humans. Seasons would still be massively impacted. The tilt of our planet would become secondary to the distance to this second star. When the second star is as far away as possible and a hemisphere on Earth was also experiencing winter, it would get extremely cold. On the other hand, combine a summer with the second star passing as closely as possible, and it would be incredibly hot. A curious phenomenon with red dwarfs is that they also produce huge flares, much larger than the ones our own sun produces. They would easily knock our satellites offline on a regular basis. Earth would have some spectacular auroras, but our power grid would be under serious threat. So, even with the smallest type of star habitability on Earth would be under serious threat. Increase the mass of the second star and you begin to get additional problems, like increased ultraviolet radiation making going outside more and more dangerous. You would also have two shadows a lot of the time. Once you turn that second star into something like a blue supergiant, there really would not be a place in the system where there is even a hope of habitability. Blue supergiants can be many times the mass of our Sun and millions of times more luminous. Their devastating stellar winds would be enough to rip our atmosphere away over a relatively short period of time. Larger still are red supergiants, the biggest stars in existence. If you were to place the largest known of these stars directly into the center of our solar system, it would encompass everything up until the orbit of Saturn. However, there is a scenario where we could be in a binary star system with a supergiant and still be on a habitable planet. You see, binary stars can orbit very far apart, taking thousands of years to complete one orbit. The most extreme cases can see a separation of over 1 light year. What can happen is that planetary systems form around each of these stars separately. This would mean that if Earth was in one of these planetary systems, it would only have one parent star. The second star would be easily visible in the night sky, but might not make much of an impact during the day. The big problem with having a supergiant on your doorstep, even a light year away, is that it is a ticking time bomb. Supergiants tend to be on the verge of erupting in a supernova. A supernova going off only 1 light year away would be catastrophic, probably sterilizing the entire planet as radiation from the shockwave passes over. The good news is that we do not know of any star capable of erupting in a supernova within 100 light years of us. Going back to the single parent star configuration, even with a second sun far outside our orbit, it would still mess with our day and night cycle pretty badly. There would only be tiny parts of the year where you would get a proper day and night. As the year progresses, you would get less and less of a night, until at one point, you would have no night at all. So while having a second sun during a sunset seems like it could be an amazing prospect at first glance, delving into the details reveals that we are extremely lucky to only have the one. No matter what configuration you look at, there are major problems. So let us be grateful for our boring but steady and safe star, the Sun. Long may it continue to be so. And even though it is relatively close to us and not exactly hard to spot, there is still a lot we do not know about it. Which is why in recent years, both NASA and the European Space Agency have sent spacecraft to study the Sun closer than we have ever been before. These missions will be the closest we have ever been to our star. So close, in fact, that they will be able to directly interact with its atmosphere. It is surprisingly difficult to get a probe into a close orbit around the Sun. It takes 55 times more energy to go to the Sun than it does to go to Mars. You see, the Earth is always moving sideways relative to the Sun at a very high speed. In order for a probe to successfully enter into an orbit around the Sun, it must cancel out almost all of that sideways motion. This is why these probes were launched using two of the most powerful launch vehicles available. NASA's Parker Solar Probe will use 7 Venus flybys over nearly 7 years to gradually shrink its orbit around the Sun. At its closest point, it will only be about 6 million kilometers away, which is deep inside the Sun's corona. Being that close would feel like having 500 suns in the sky, with the temperature reaching up to 1400 degrees Celsius. To protect the spacecraft and all its equipment, it is shielded by a thick carbon composite shield. This spacecraft is by necessity as autonomous as a space mission has ever been. For large sections of its orbit, it will not be able to point its antenna at Earth, so it will have to control itself, format its own data, and archive it until it can communicate with us again. The European Space Agency's solar orbiter will also use gravity assists from Venus as well as Earth. It will reach its closest approach to the Sun every 6 months at around 43 million kilometers away. This is comparatively much further away than the Parker probe's closest approaches, but the temperature can still reach up to 500 degrees Celsius. The solar orbiter is protected by a heat shield made with titanium foil layers. The objectives of both missions are similar. They aim to find out more about our Sun's corona, its solar winds, coronal mass ejections, the structure of its magnetic field, and simply how it all fits together. The strange thing about the Sun's corona is that its temperature is between 1 and 3 million degrees Celsius, whereas the Sun's surface temperature is only about 5,500 degrees. And currently, we do not really know why. These probes will help us understand. The Parker probe is going deep into the corona where no man-made object has gone before. It has instruments that can directly sample and collect data about the particles that exist there. The solar orbiter, on the other hand, carries both particle detectors and telescopes. It can take close-up pictures of the solar landscape, and due to its orbit, it will be able to track a region of the solar atmosphere for much longer than is possible from Earth. It will be able to observe storms building up over several days. And so these two probes are complementary. Both will help further our understanding of the Sun's corona in their own quiet way. Already the data sent back from the Parker probe is helping our understanding of how the Sun's magnetic field and the corona interact to form the solar winds. It has also discovered evidence of a dust-free zone close to the Sun, where cosmic dust particles are vaporized by the sun's radiation. The solar orbiter has sent back its first images, and scientists found something they called campfires, tiny explosions on the sun's surface that occur as a result of disturbances in small magnetic fields. These probes are our messengers, our eyes and hands, reaching out to touch the fiery breath of our star and bring its secrets back home to us. The sun is a quiet, steady presence in our lives. But for a star, our sun is relatively stable. A type of star known as a yellow dwarf. It is middle-aged and has not changed dramatically for the last 4 billion years. We can be glad our sun is as stable as it is, as unlike most other stars. The energy it emits is fairly constant. But if you were to look at footage of the sun taken by the Solar Dynamics Observatory, you would quickly realize that even one of the most stable types of star has a landscape of constant activity. As we have seen, the sun is a giant, nearly perfect sphere of plasma, composed mainly of hydrogen and helium. At its core, under immense pressure, hydrogen atoms are fused together to become helium. This nuclear fusion is the source of all the sun's energy. On average, it takes a photon of light 170,000 years to travel from the core through the dense radiative zone to the next layer, the convective zone. Here, hot material rises to the surface, cools, and then sinks back down in a constant churning motion. This convection is what brings the energy to the surface, where it glows like any hot material does. Plasma is an extremely good conductor of electricity and is also affected strongly by magnetic fields. Sunspots, as we know, are the surface representation of these magnetic fields. The fields get very tangled below the surface between the radiative and convective zones. When they rise, they tend to appear in pairs with a positive and a negative polarity, just like a magnet. The strongest magnetic fields we observe are in the sunspots, and these sunspots can be enormous, multiple times the size of our Earth. They can often be seen at the base of various other solar phenomena. The great coronal loops, the bright prominences, and the sudden sharp solar flares. These flares tend to happen over active regions which are essentially sunspot groups. An event called magnetic reconnection is what produces the energy that causes both flares and coronal mass ejections. Because the convective zone is very turbulent, the magnetic fields are constantly being twisted and braided, creating complex structures. It is within these structures that magnetic energy is stored. Imagine the magnetic field as a rubber band. You twist it and turn it, and then, at some point, you pull it too strongly, and it breaks. That is essentially when we have a reconnection event. The magnetic field lines reconnect, and when that happens, a lot of energy is released, the equivalent of millions of nuclear bombs, all in one instant. That energy will produce both a solar flare where large amounts of radiation are released and also potentially led to a large-scale movement of the material that was suspended in prominences. A lot of it will move back towards the sun. But in the middle of these magnetic fields, a bubble of material is often ejected away from the sun. Millions of tons of charged material flying out from the sun at hundreds or even thousands of kilometers per second. These are the coronal mass ejections, or CMEs. These CMEs come in contact with the planets all the time. Earth, as we know, is protected by its relatively strong magnetic field. But when the Earth is hit by a CME, this is called a geomagnetic or a solar storm. During such a storm, Earth's magnetic field gets somewhat compressed by the force of the CME. Normally, this has not been a problem for people with their feet firmly on land. But what would happen if the most powerful solar storm ever recorded were to hit Earth today? To find out what is believed to be the most powerful CME in recorded history, we have to go back to 1859, to a solar storm known as the Carrington event. From the 28th of August to the 2nd of September of that year, many sunspots appeared on the sun in one place. On the 1st of September, 2 amateur astronomers separately saw and recorded an extremely bright solar flare. This flare was connected to a major coronal mass ejection that traveled directly towards Earth, taking only 17.6 hours to make the journey, much faster than the speed of normal CMEs, which typically take several days. It is thought that the high speed of this one was made possible by a prior CME, which would have cleared any ambient solar wind plasma out of the way for the Carrington event. On the 1st and 2nd of September, the largest recorded geomagnetic storm occurred. Auroras were seen around the world as far south as the Caribbean. The aurora over the Rocky Mountains was so bright that the green glow woke local gold miners who began making breakfast as they believed it was morning. It was reported that people in the northeastern United States could still read a newspaper by the aurora's light. This is unprecedented, as typically auroras are not visible at these middle latitudes. A consequence of this storm was that the electrically charged particles from the sun surged telegraph systems all over Europe and North America, causing them to fail, and in some cases, giving the telegraph operators electric shocks. Telegraph pylons threw sparks from the charged atmosphere. And amazingly, some telegraph operators could still continue to send and receive messages, even though they had disconnected their power supplies. The storm was comparable to a hemisphere-wide EMP bomb fairly harmless to humans but extremely bad for electronics. Today, if a CME the size of the Carrington event or bigger were to hit Earth, the consequences would be far more disastrous. We now have satellites and space computers, telecommunications, and power plants that would all be severely damaged. The most susceptible technologies are the electricity grid and telecommunications, which have cables stretched out over a large distance. Without proper safeguards in place, transformers on the power grid could break, and millions upon millions would be without power for a lengthy period of time. It could take years to replace them, as transformers are often tailor-made for their specific requirements and are not mass-produced. Without power, refrigerators would not be able to stop food from spoiling. Payment systems that rely on credit cards would not work. People would not have access to the internet. Hospitals would struggle when their backup generators ran out of fuel. We would be completely cut off from the outside world. An independent think tank recently put the cost of damages to the USA alone at $2.6 trillion. The think tank placed the estimated recovery time to repair the damage at 4 to 10 years, and estimated that 2/3 of the US population could die of starvation disease and the chaos that would follow during that time. We have had some very near misses. A Carrington-sized event could have been a reality in 2012, where a huge CME was ejected from the sun. It missed us by a margin of 9 days. Had it been 9 days later, Earth would have been a bit further in its orbit and directly in the CME's path. As far as we know, a CME even bigger than the Carrington event could hit us tomorrow, or the next one could be in a few thousand years. Since 1995, NASA has placed a telescope in orbit which is constantly monitoring the sun for CMEs. As light travels much faster than a CME, this would roughly give us about 71 hours warning before it hit. This might be enough time to turn off some of the power stations, thus protecting the electricity grids. The US is currently the only country to have such a program in place. Other countries are working on temporary transformers which are quicker to produce and are proposing upgrades to their power grids that would not allow a surge of electricity to destroy the network. This process, however, is slow. It seems countries are in no rush to foot the bill. And so until mankind is prepared for a CME, we really are at the mercy of our life-giver star. And this star, our sun, holds an almost unimaginable amount of energy. Compared to what we gain from fossil fuels, the sun produces a staggering amount. Even if you are only considering the amount of light that hits our planet's surface directly, we would receive around 10,000 times the energy we are currently using from oil. More than enough to cover our needs. Obviously, capturing all of that sunlight is a bit tricky to do in practice. And if we were to capture all of it, that would make life a bit difficult for any plants on the planet wanting to use that light for photosynthesizing purposes. But even if we got to the point where we were only using half of all that available energy, we would completely remove our need for fossil fuels and could have the energy necessary to support a significantly larger population. Looking to the future, that might be something we need to consider. Reaching a population of 40 trillion people is actually not that far off, at least on the scale of human history. At our current rate of growth, it could happen in only 800 to 900 years. So what might be the solution when that happens? Why doing as a theoretical physicist named Freeman Dyson once hypothesized that alien races might do, increasing the amount of solar energy that we capture, probably by building solar panels or mirrors and sending them into orbit around the sun. Dyson was considering the way hypothetical alien civilizations might try to power their society and how we might spot them. He thought that if an alien race was spacefaring, they might build a habitat in space near their local star to take advantage of its solar radiation. Over time, more and more habitats would be built until one day, most or all of the star would end up surrounded by a truly mammoth shell of habitats, which would capture and utilize all the radiation the star was emitting. This shell came to be known as a Dyson sphere. Creating one would give a species access to a ridiculous amount of energy, sending their civilization into the next stage up in galactic exploration and expansion. This idea does sound a little like something out of science fiction. But a Dyson sphere or a Dyson swarm as a segmented configuration of panels or mirrors is technically known offers power that is many orders of magnitude higher than what we can do with just a planet's worth of surface area. If we were to complete such a structure, we would increase our energy levels by 20 trillion times. That should be enough to keep the lights on for the foreseeable future. Technologically speaking, we are pretty much at the point where we could make a solar panel that could capture sunlight from the sun and send it towards Earth. Or even easier, we could simply create space mirrors to reflect the light towards where we needed it. Placing mirrors into stable orbits is not impossible for us, and having them be able to maneuver slightly to reorient through the year does not sound too implausible. So then, it is just a question of how much material this would require. Unsurprisingly, a Dyson sphere would need a lot of material. Building one that coincided with Earth's orbit would need about 6% of the entire volume of our planet, even if the panels were less than a millimeter thick. This is hardly ideal. But if we instead built the sphere at a much more compact distance from the Sun, say at the distance of Mercury's orbit, then the material requirements become much more feasible. Mercury itself contains all the raw material that might be needed for such a structure. And as far as we know, there is no one living on Mercury who would complain if we were to fill it with holes. But then there is the last issue to consider. It is an energy-intensive process. Materials have to be mined, processed, then made into their components. And even once that is done, they need to be lifted out of Mercury's gravity well. If we utilized all the sun's energy that was hitting the planet Earth and spent it all on doing nothing but lifting mirrors for our Dyson sphere out of Mercury's orbit, we can calculate how long it would take us to lift enough mirrors to complete the entire shell. The process would take about 425,000 years, during which time there would be no energy left to support Earth's population or give light to our plants. Maybe this is not such a viable idea after all. But wait, there is one last point to factor into this. Once our first mirrors came online, they could start providing energy of their own to help pay the energy costs. This would then become an exponential process. One mirror would provide the energy to make a second, then both would double to make 4. According to some calculations, Mercury would be completely disassembled in as little as 31 years. In other words, if we started building right now, you might live to see its completion. Such numbers really bring into focus the viability of this project. Something that takes half a lifetime to complete is certainly ambitious, and the initial cost would indeed be great. But there are not very many technical barriers left towards attaining the immense energy of the sun. A Dyson sphere might well be another example of something that sounded like science fiction to us, but will turn out to be something our children or grandchildren's will one day come to take for granted. And as we imagine this great sphere of mirrors reflecting the sun's light in a controlled, beautiful dance, we are reminded of the other great dances of light and shadow in our solar system. The eclipses. In the middle of the day, the sky starts to darken. It is as if dusk has fallen early. People look up and notice something is happening to the sun. A dark shadow moves before it, gradually devouring every last trace of brightness, until our familiar light bringer is only a shimmering, ghostly ring around a pitch-black orb. A total eclipse is occurring. This will soon be a reality for the continent of North America in April of 2024. But America is not the single place eclipses happen, and neither is Earth. There is something special about an eclipse here on our planet. By a bizarre but highly fortunate cosmic coincidence, the moon is the right size and distance from us, that its angular diameter is almost identical in size and shape to the angular diameter of the sun in our sky. This leaves for an impressive spectacle, where the corona of the sun creates a ghostly aura around the moon. Looking closely around the edge of a total solar eclipse, You can also see the silhouette of the moon's craters and reddish wisps coming off from the sun. These are the prominences, millions of tons of charged particles suspended in the sun's atmosphere by powerful magnetic fields. During an eclipse here on Earth, the moon casts a shadow about 250 kilometers in diameter, which moves across the Earth as the moon orbits. The shadow moves extremely fast at roughly 1 kilometer a second. Witnessed from a high altitude, it is a majestic sight as the shadow shifts across the landscape. The shadow is not as sharp as you might expect. This is due to the angular diameter of the sun and the moon and their distance apart. The umbra is the shadow where the sun is completely obscured, and the penumbra is the shadow where the moon only partially obscures it. This part of the shadow is much wider than the 250-kilometer wide umbra shadow. The moon does not create an eclipse every month when it orbits in front of the sun, because its orbit is not in line with the Earth's orbit around the sun. This means there are only a couple of times per year when the alignment is just right. This alignment of three celestial objects is known as a syzygy. But the Earth is not the only place to experience solar eclipses. If the moon can occult the Earth, then surely the Earth can occult the sun from the moon's perspective. And the answer is yes. But it is not the shadow that is the really visually appealing part of this from the Earth anyway. This is because the Earth is 4 times as big in the moon's sky as the moon is on Earth. So when the Earth fully obscures the sun, the whole moon is in the umbra. But what is different this way around is that unlike the moon, the Earth has an atmosphere. This means that when the moon is totally eclipsed, the Earth's atmosphere reflects the sun's light around the planet, gently illuminating the moon in a reddish hue. This makes for a beautiful but almost spooky view. The color is caused by Rayleigh scattering the same process that makes our sky blue and our sunsets red. From the moon's perspective, none of the sun would be visible during a total eclipse, but the atmosphere on Earth would be illuminated so you would see a ring around it. An actual view of this, taken by a Japanese probe in 2009, is quite an awe-inspiring sight. The Earth and Moon are not just getting in the way of each other. The Moon often makes an appearance in front of the Sun from the perspective of our sun-observing satellites. Mercury and Venus also transit across the Sun, their tiny silhouettes appearing as small black dots. These transits are how we are able to detect planets orbiting other stars. Telescopes measure the brightness of distant stars, and if a star continually dims in a pattern, we know that a planet is orbiting that star. Using this method, we have discovered over 3,000 exoplanets. It can even help scientists calculate the size of the planet and the composition of its atmosphere. by looking at the spectra of the light that passes through. Moving to another planet, we can go to Mars, which has two small moons, Phobos and Deimos. The Curiosity rover was able to capture a moment where, incredibly, Phobos eclipsed Deimos. It was also able to see a transit of Phobos in front of the Sun. These solar eclipses on Mars do not last for more than about 30 seconds, and the surrounding ground gets noticeably darker. On Jupiter, its 4 large moons can transit the planet, sometimes 3 at a time, leaving 3 big shadows. Cassini saw some incredible transits and occultations of Saturn's many moons. And as New Horizons whizzed by Pluto in 2015, it turned its camera back to capture the dwarf planet, totally eclipsing the Sun. What it saw was dazzling. The sunlight streaming through and illuminating Pluto's atmosphere, and its haze layers with the ridges and mountains on its surface, highlighted by the stark contrast of its night side. These fleeting moments, when one celestial body brushes lightly against another, even if it is only through their shadows, are filled with a special beauty. They remind me how connected the universe is, even across thousands, millions, or even billions of kilometers of space. The darkness of an eclipse is a peaceful, fleeting thing. But our own planet has a different kind of shadow, a pollution problem. There are the plastics and landfill items, the types of things you might throw out at home. And then there is the dangerous industrial waste, like nuclear byproducts, biohazards, and chemical toxins. So far, the best solution we have been able to come up with for disposing of nuclear waste is burying it deep underground. Not ideal when you consider that the stuff remains dangerously radioactive for tens of thousands of years. So why don't we just strap it to a rocket and blast it into the Sun? To begin answering that question, it is actually really hard to crash anything into the Sun. Let us take a closer look. Suppose we have gathered together a massive pile of toxic waste destined for our star. The first thing we would need to figure out is how to get it into space. To get our trash back through the atmosphere and out past Earth's orbit, we would need to accelerate it to a velocity of 2 kilometers per second. This is the speed known as escape velocity. Once free of Earth's orbit, our garbage craft is on course for a solar collision, right? Wrong. Once our package escapes Earth's orbit, it is still gravitationally bound to the Sun. Put super simply, Earth and everything on it is moving sideways relative to the Sun at 30 kilometers per second. Combining this sideways motion with the gravitational pull of the Sun is what keeps us locked in an orbit. So to make our garbage fall into the Sun, we would need to lose that sideways motion. There are 2 options. The first is to bring up enough fuel to break in space. This would mean configuring our garbage payload's propulsion system to generate thrust opposite to its direction of sideways motion. This cancels out the sideways motion, slowing the spacecraft down and letting the sun's gravity do its thing. Earth orbits the sun at 30 kilometers per second. So to break a garbage rocket launched from Earth, you would need to be able to accelerate 30 kilometers per second in the opposite direction. The problem is, it is simply too much fuel. The Saturn V rocket that took men to the moon needed 2 million liters of fuel just to leave Earth's orbit. A mission like this would require orders of magnitude more. No modern rocket technology would even come close to being able to carry the amount needed. Okay, so scenario 1 is out. What other options have we got? Another way to decelerate in space is with a gravity assist. Usually, when we talk about gravity assists, we are thinking of the kind that slingshot the Voyager probes into the outer solar system. However, gravity assists are not only used to speed probes up, they can also slow them down. If you were to approach a planet from behind, fly in front of it, and exit behind it, your spacecraft loses energy, while the planet gains energy. The thing is, this takes a lot of time. One mission using this technique was launched in 2018 and will only arrive into orbit around Mercury in 2025. This is because to slow down enough, one gravitational assist will not do. In fact, it needs 9 different gravity assists. Crashing our garbage into the sun would be a similar game of carefully calculated orbital mechanics. So it is possible, but is it worth the time, effort, risk, and technical challenges? Probably not. Think about what could go wrong. First of all, we are proposing packing a bunch of nuclear waste onto a rocket and launching it from Earth. A launch failure or explosion could be disastrous. Even the world's most successful rocket has a 2 to 3% failure rate. I do not know about you, but when nuclear waste is at play, I do not like those odds. Even if the launch goes well, the project itself would be ridiculously expensive. And lastly, it would actually be easier, quicker, and cheaper, but still crazy expensive to shoot our garbage out of the solar system toward interstellar space. So there you have it. We do not shoot garbage into the sun because it is super hard, super risky, and super expensive. We are probably better off being more conscious about what we consume and how we recycle it. And as our dream of the sun comes to a close, we are left with a feeling of quiet gratitude. Gratitude for this one steady star, a fiery heart that holds us in its gentle gravitational embrace. Its light travels through the silent dark to warm our world. Its rhythms pulse through our very being, and its mysteries continue to fill us with a gentle, sleeping wonder. Its story is still being written in every ray of light, in every solar flare, in every quiet dawn. And as we drift off to sleep, we can carry a piece of that story with us. a dream of the sun burning brightly and peacefully at the center of our quiet sleeping world. The thought widens, becoming air, and here our journey ends. The dream of the sun dissolves back into the quiet darkness of the night sky, leaving only a soft warmth behind. The stories are told, the light has traveled its long path, and now there is only stillness. Rest now, gentle listener. Let the silence hold you, and may your own dreams be as peaceful as a star shining steadily in the vast and gentle dark. Sleep well.